Let's look at some more definite integrals. Specifically, this first example is the integral from 0 to pi of sine x minus 2. In this video, I'm not generating graphs. If you wanted to generate the graph of sine x minus 2 in your graphing calculator, go into the y equals screen, type in sine x minus 2, and then hit your zoom button and number 7 for trig settings. If you're in degree mode, the x-axis will be in degrees from negative 360 to 360. If you're in radian mode, the x-axis will be marked from negative 2 pi to positive 2 pi. This is the sine curve shifted down 2 units. We don't have to have the graph to find these net areas. So let's jump right in. Sine x, its antiderivative is negative cosine x. And that's because the derivative of negative cosine x is positive sine. Negative 2 has an antiderivative of negative 2x. Evaluating the antiderivative at pi minus evaluating the antiderivative at 0, that gives us negative cosine of pi minus 2 pi. From your unit circle, cosine of pi is negative 1. Two negatives make a positive 1 minus 2 pi. In the back bracket, where we substitute in 0, we have minus cosine of 0 minus 2 times 0. Cosine of 0 is positive 1, so that's negative 1 minus 0. And overall, that negative and that negative make a positive 1. Combining like terms, we have 2 minus 2 pi area. That's the exact area. If you put that in the calculator and round it to a few decimal places, then that's the approximate area between the function and the x-axis between these two values, 0 and pi. Our second example we did in class was the integral from 0 to pi over 4 of 7 minus 7 sine squared theta divided by 3 cosine squared theta. Now, there's a Pythagorean identity in your trig class that you learned that was sine squared theta plus cosine squared theta equals 1. In purple down here, or magenta, whatever color that is, if you were to subtract one of your two trig functions over, for example, if you subtracted sine squared theta from both sides, your identity would turn into cosine squared theta equals 1 minus sine squared theta. Well, after we factor a 7 out of the numerator, that's what I did on this step, we factor a 7 out, that leaves 1 minus sine squared theta. You can make a direct cancellation because those are equal. That leaves 7/3 behind the integral. So we're going to integrate from 0 to pi over 4, just simply 7/3. Well, that's a constant, and so its antiderivative, you just attach the variable to it, 7/3 theta. Evaluated at pi over 4, minus, and then evaluated at 0. 7/3 times 0 is 0, so the only calculation we really need to make is right here in the front, 7 pi over 12. That's the exact area between this function and the x-axis, the net area, if some's above or some of it is below, but that's your net area for this function between these two angles. The third example we did on this worksheet, we integrated from negative pi over 6 to positive pi over 6, 4 secant squared x dx. The antiderivative of secant squared x is tangent x. The derivative of tangent x is secant squared x, so that's the antiderivative. The 4, you can easily pull that in front of your integral, or you can just leave it there. The derivative of 4 tangent x is 4 secant squared x. So that's the correct antiderivative. Substitute pi over 6 in, and then minus, and then substitute negative pi over 6 in. Tangent of pi over 6, if you remember from your trig class, the unit circle, it's the sine value divided by the cosine value. with an ordered pair, it's the y-coordinate divided by the x-coordinate. So at pi over 6, the y-coordinate is 1/2. The x-coordinate is square root of 3 over 2. That divides out to a value of 1 over square root of 3. Tangent of negative pi over 6 takes you to a location with a y-coordinate of -1/2 and an x-coordinate of positive square root of 3 over 2, because that's negative 30 degrees equivalent. And it has a y over x ratio of -1 over square root of 3. These two negatives make a positive, so inside the bracket we have 2 over square root of 3. Multiplying by that scalar 4, that gives us 8 over square root of 3. If you wanted to rationalize and multiply top and bottom of the fraction by square root of 3, this is the rationalized form. Either number is fine with me. I don't care if they're rationalized or not. And if you're using WebAssign, a Cengage product, it doesn't care either. The next example we did in class was the integral from -3 to 3 of e to the theta plus sine theta. This should actually be a theta instead of an x. That was just my bad on a typo. I'm going to fix it here. That actually is important when you get into multiple variable calculus and take integrals. You actually have to make sure those variables match. Anyway, that was just my bad. It was a typo, so I fixed it. E to the theta has an antiderivative of e to the theta. Sine theta has an antiderivative of negative cosine theta. So this is the antiderivative of this function. Evaluated at the top limit 3, that goes in for your thetas, minus, and then evaluated at the lower limit, -3. That gives us e cubed minus cosine of 3 minus e to the -3. You can write that as 1 over e to the positive 3. It doesn't matter to me. You can leave it in this form. That's totally fine with me. Because cosine is an even function, if you take a negative angle and its positive version, for example, like a negative pi over 2 and a positive pi over 2, cosine is going to have the same x value on the unit circle. That's called an even function when the angle is negative or positive. Either way, you get the same value. Anyway, long story short, we can change this -3 to a +3 because cosine is an even function. Distributing the negative sign, that's going to give us e cubed minus cosine 3 minus e to the -3 plus cosine of 3. Well, the second and fourth term are opposite, so they cancel, leaving us with e cubed minus e to the -3. It is totally appropriate if you want to write this as e cubed minus 1 over e cubed. That is up to you. So you can either leave it in the original format with the powers of -3, or you can transfer it to the bottom of the fraction and the 3 becomes positive. I hope this video helps. If you have trouble, reach out, phone or email, swing by the office if you're on campus, and I'll do my best to help you out.